Okay everybody, so let's get started. Okay, so normally the advice is to not start on these multiple choice because they require you to know all the topics together. The advice is normally to go to the main questions and warm yourself up and then come back to the multiple choice. But we're going to wait in here like fools. So a particle completes 6 revolutions in 4 seconds, angular velocity in rads per second. So to get rads per second, we need to divide a total number of radians by a total number of seconds. Now, we already have a time in seconds, so that's fine, but we need to convert 6 revolutions into radians. Now, there's 2 pi radians in a circle, so it's going to be 6 times 2 pi over 4. So 6 times 2 pi over 4, which is 12 pi over 4, which is 3 pi. There's only one number that matches that. We know that pi is 3.14, so this is going to be 9 or so. B. Okay, so which of the following is equivalent to the unit for energy? Okay, so we remember that work is force times distance. We can see that force could come into these equations here. And of course F is ma, so we're talking m times a times d. So that's going to be like kilogram meter per second squared times meters, which is going to be kilogram meter squared seconds to the minus 2, which is a. Right, so a radium nucleus decays by emitting an alpha particle. The speed of the recoiling nucleus is small compared to the speed of the alpha particle. This is because... Okay, so force acting on the recoiling nucleus is smaller than the force acting on the alpha particle. No, that's nonsense, because the third law requires the force on each object to be the same. Momentum is mainly concentrated in the alpha particle. No, the momentum transferred to one object will be exactly the same as the momentum transferred to the other object. Again, that's required by the third law. Momentum of recoiling nucleus is smaller than the momentum of the alpha particle. That's sort of the reverse of what the question is telling us. Recoiling nucleus has a much larger mass than the alpha particle. That's what we're after. Larger mass, therefore it doesn't have to move as fast to have the same momentum as the other object. Okay, so that's D. Okay, potential difference across capacitor is V. The energy stored on the capacitor is X joules. Potential difference across the capacitor is increased to 3 times V. The energy stored is now what? Okay, so crucially, the energy in a capacitor is a half CV squared, so it's proportional to V squared, with everything else constant there. So we've gone from a value V heading towards a value of 3V. So the energy will have gone from being related to V squared to being related to 3V all squared, which is 9V squared. So it's 9 times what it was before. So if it was X before, it'll be 9 times X now. C. Figure 1 shows a vertical plane coil of 50 turns carrying a current of 3 amps. The length of each side of the coil is 4 centimeters. Figure 2 shows a view of this coil from above within a horizontal magnetic field of flux density 0.2 Tesla. Okay, so this current direction that they give us in the first part, allows us to work out that the current in the vertical bits are going to be like that. Okay, that means at QS, this point here, we've got current coming up. So I'll just use the point of an arrow convention. So we've got current coming towards us. We've got magnetic field pointing that way. well, crucially, those two are at right angles to each other, even though the plane of the coil isn't at right angles to the field that particular conductor is. So we can use BIL. Okay, however, we have to multiply by the 50 because it says there are 50 turns. That means there'll be 50 strands vertical here, each of 4 centimeters. So the total L will be 50 times 4 centimeters, and that gives us 1.2 newtons. Question 6 then, an electron gun uses a potential difference to accelerate electrons from rest to a speed of 2 times 10 to the 7 meters per second. Potential difference is how much? So the electrical work done on the particle will be Q times V, and that will be equal to half mv squared. We're reasonably below the speed of light, so we shouldn't have to mess about with anything else. So that will give us V of mv squared over 2Q, where Q is the charge of an electron and M is the mass of an electron from your formula sheet. So you would need to go and look those up in the formula sheet and put them through the calculator. Better to write them down. So I'm getting like 1137. 0.5 using those numbers, so it'll be B, won't it? Okay, so now they want to know the de Broglie wavelength associated with electrons moving at this speed. So de Broglie told us that lambda was h over the momentum, and so that's going to be like 6.6 times 10 to the minus 34 over the mass of the electron, 9.1 times 10 to the minus 31 times the speed, 2 times 10 to the 7. Okay, so that gives us 3.62 times 10 to the minus 11 meters, so that'll be this one. Right, so a particle detector shows tracks produced by two particles X and Y that were created by the decay of a lambda particle at O. So which of these is a valid conclusion? X is a negatively charged particle, don't know the magnetic field. Y is a positively charged particle, don't know the magnetic field. The lambda particle is neutral, while X and Y go opposite ways. The magnetic field is acting into the plane of the paper. There's nothing that is absolutely certain except for the fact that these two curve opposite ways. So C. Which of the following is a correct statement about momentum at the decay? The vector sum of the momenta of X and Y must equal that of the lambda particle. Sounds pretty good to me. The momentum of X is equal to that of Y. No, there's not a requirement for that. Total momentum of the system is 0. No, because it's sort of moving towards the top right, so it has momentum. The vector sum of the momenta of X and Y must equal 0, and the vector sum of those two must equal the particle that created them. So it's A. So which is a correct statement about energy then? Energy of X must be greater than that of Y. No. Combined energy of X and Y must be more than the energy of the lambda particle. No. Mass of the lambda particle must equal the combined energy of X and Y. No, because the lambda particle would have also had kinetic energy. The mass energy of the lambda particle must equal the total energy of X and Y. Okay, so the mass energy of the lambda particle plus its kinetic energy equals total energy of X and Y. So that'll have to do. Alright. Question 8 wants a description of Rutherford's observations in the alpha particle experiment. I'm not going to go into detail here, but you know the kind of things that we're looking for. Rutherford took this piece of gold and he fired awful particles at it. Most of them go straight through. Some of them are deflected a little. Tiny amount are deflected through very large angles. The idea is that most go straight through, therefore whatever the few that were deflected were hitting, it was very tiny. The fact that it could send it back the way it came meant that there was a repulsion from another positive thing, so that whatever they were hitting was positive. So the conclusions you get from that is that whatever it was in there, it was very small, very hard to hit, most of them going straight through. The ones going straight through sort of are telling us that most of the material in there is concentrated in very tiny locations, and therefore most of the atom is emptiness, empty space. The nucleus is very, very tiny. It's positive, and almost all of the mass of the atom is contained there. The alpha particle, to be turned through 180 degrees, had to find something that had a hell of a lot more mass than it. And so, tiny, massive object at the centre, and by massive I mean containing lots of mass, it's not contradicting tiny. Tiny concentration of mass at the centre of the atom, and most of the rest of the space is just nothing. That's what Rutherford gave us, this idea of a tiny dot, and that's far too big. The actual dot would be less than a pixel on that diagram. Most of the mass being in that wee centre spot, and most of the space being unoccupied. So, 1.5 volt cell is connected to a switch S, neon lamp and a coil which has many turns, as shown. Nothing is observed when the switch is closed, but the neon lamp flashes as soon as it is opened. The neon lamp flashes when a potential difference across it is about 200 volts. So, you get nothing as you turn it on, because you're really only dealing, when you're turning it on, you're really only dealing with the voltage of the cell. However, when you turn it off, the magnetic field produced in the coil collapses. And the collapse of this field, as you turn the system off, produces a flux linkage as it dies away with the coil. And the many turns then produces a large EMF which appears across the neon lamp and causes it to flash. And it comes down to the fact that the magnetic field collapses very rapidly when you disconnect the electricity. So you get a very high rate of change of flux, which produces a high EMF. Question 10 shows us this liquid crystal display and explains that they're made up of two parallel glass plates 10 micrometers apart with liquid crystal molecules between them. The glass is coated with a conducting material. The molecules are positive at one end and negative at the other end. They are normally aligned parallel to the glass plates as shown. Switch S is closed and 1.5 volts is applied across the glass plates. Calculate the electric field strength. So electric field strength in this kind of parallel plate situation is easily calculated from V over D. And that gives us 150,000 volts per meter, or 1.5 times 10 to the 5 volts per meter. Don't forget your units. So now they're saying what happens to the molecules. Well, you've got a positive plate here, you've got a negative plate down here, and you've got a molecule which has a, you can see here, positive end and a negative end, with the positive end here and the negative end there. So it's going to rotate with its positive end uppermost. I mean, from that position it's going to turn clockwise. That's what you need to explain. So it'll rotate until it's in that position. Question 11. Diagram shows a proton. Draw lines to represent its electric field. Okay, so field's going to radiate out. Try and keep them even when you draw them, and try and draw them straight. I'm drawing on an iPad, so I get a little bit of leeway for wobbly lines, but you should be using a ruler. Remember, I mentioned the ruler on the front of the paper. Don't forget that. So now they want us to calculate the electrostatic force on the electron in a hydrogen atom if the average distance between the proton and the electron is 5.4 times 10 to the minus 11. Well, this is going to be Coulomb's law. So that's your calculation. And that's your answer. Okay, King Decab was the highest roller coaster in 2007. Trains initially propelled along a horizontal track by a hydraulic system. It reaches 57 meters per second in 3.5 seconds, then climbs a vertical tower and goes back to the ground. Calculate the average force used to accelerate a fully loaded train along a horizontal track. Well, this is the modified or Newton's version of the second law, where F is mv minus u over t. And since mu is nothing, it's just going to be mv over t. So that's going to be like 12,000 times 57 minus 0, because mu is going to be nothing, over 3.5 seconds. And that gives us 195429 newtons. Okay, sorry, I should have really put the answer down here. Sorry about that. It says point X on the right is just before the train leaves the horizontal track and moves into the first bend. Complete free body diagram to show the two forces acting on the rider in the train at this point. It's still moving horizontally, so you're going to have the person's weight, and you're going to have some kind of normal reaction from the seat. And you need to say what those are, not just letters. Mass of the rider is m, and g is acceleration of freefall. Just after point X, the reaction force of the train on the rider is 4 mg and can be assumed to be vertical. This is referred to as g-force of 4g. Show that the radius of curvature of the track at this point is about 100 meters. So it's heading this way. We've got r pointing up and mg pointing down. And it's the reaction force that has this value of 4g. That means that it's extra value of 3g, since there's a g pointing down, 4g pointing up, there's a net upward force of 3g. 4mg pointing up, mg pointing down. So we write resultant force towards the centre equal to mv squared over r, which is the amount of force required towards the centre to make it move in a circle. So 4mg minus mg equals mv squared over r. So 3mg equals mv squared over r. So rearranging that, we get that r is mv squared over 3mg, and the m's cancel, so it's v squared over 3g, and so that gives you an r of 110.4 meters. Show that the speed of the train as it reaches the top of the vertical tower is about 20 meters per second. Assume that the resistance forces are negligible. The height of the tower is 139 meters. Okay, so we conserve energy then. The kinetic energy at the bottom will equal the kinetic and potential energies at the 139 meters. Or another way of saying that is that the change in potential energy will equal the change in kinetic energy. And again, you can cancel m out of this. Okay, so v squared is going to be u squared minus 2gh. So v is going to be the root of all of this. And that gives like 22.8 meters per second. Okay, riders will feel momentarily weightless if the vertical reaction force becomes zero, and a track is designed so that this happens at point Y. So what they're basically saying is if you go over the top of this thing at 22.8 meters per second, you're going to be weightless. So just remember, you need to have mv squared over r towards the centre of a circle to move in that circle. And we're putting the resultant force towards the centre of mg, which is towards the centre, minus r, which points away, equal to mv squared over r. And remember, in our special case, when you become weightless, the reaction from the seat on your body will go to zero. So in that case, mg will equal mv squared over r. Cancel the m's, you've got g equals v squared over r. And consequently, r will equal v squared over g. So 22.8 squared divided by 9.81, and that gives us 53 meters. So an uncharged capacitor is connected into the circuit as shown below. Describe what happens to the capacitor when the switch S is closed. Well, you're going to have to talk about the movement of charges here. So the negative terminal of the cell will push charges onto that side of the capacitor, and the positive terminal will remove charges from the other side. So you've effectively got charges being shifted from one side of the capacitor and deposited on the other. And that will continue until the voltage on the capacitor is the same as the supply voltage, at which point the current will stop. So the current builds up voltage on the capacitor as the capacitor charges, and so the current value is always decreasing from the beginning. And that's a characteristic of charging and discharging capacitors, that the current is always highest at the beginning and zero at the end, irrespective of whether you're charging or discharging. In this case, it's being opposed by the build-up of voltage on the capacitor. Student models the behaviour of the circuit using a spreadsheet. The student uses a 100 microfarad capacitor, a 3 kilo ohm resistor and a 5 volt power supply. Switch is closed at time equal to 0. Explain how the value in C4 is calculated. Well, if you look at column C, it's just what you get if you multiply the current in B by 0.1 second, which is how long each one of these lines lasts for. So it's just Q equals IT. So we got 0.74 milliamp, T equal to 0.1 second. So it's Q equals IT from there. So 0.74 times 10 to the minus 3 times 0.1 would get you the column. Spreadsheet formula, because there's a unit change and you're also multiplying by 0.1, the overall effect would be multiplying by 100. So B4 times 100 would work as a formula. So if you're going to take the 0.74 multiplied by 10 to the minus 3 and 0.1, then you're going to divide by 10 to the minus 6 to convert it back to micro. So the equivalent of multiplying by 10 to the minus 3 and 0.1 and dividing by 10 to the minus 6, that all cancels out to the equivalent of multiplying by 100. So B4 times 100 will give you the right calculation each time. It's important in these questions to quote an equation and show the calculation with the numbers on the spreadsheet before you try and show the spreadsheet formula. Explain how E3 is calculated. Well, crucially, we've got a 100 microfarad capacitor. D3 contains the charge in microcoulombs. So if V is Q over C, then if we take what's in D3, the charge in microcoulombs, and divide by the capacitance in microfarads, then the micros are going to cancel and you're going to get the equivalent if you had divided by capacitance, charge in coulombs by farads, so you should get volts if you divide what's in D3 by 100. So D3 divided by 100 would work because the units are cancelling. Next question asks how can we tell that this graph represents the same numbers. It says show that this is consistent with the values you've calculated, or actually not the values you've calculated but just the component values in the question. So the capacitor here is 100 microfarads and the resistance is 3 kiloohms. So the time constant RC is going to be 100 times 10 to the 6 multiplied by 3 times 10 to the 3, so 100 micro times 3 kilo, and that gives us 0.3 seconds. And if we remember that that's the time for the value to fall to 37%. So by calculating 37% of the original value, we find it should have decayed to this point where the arrow is pointing at. So obviously you'll do it a little bit neater when you do it, but it's about 0.24 or 25 of a second, which is consistent with the value over here. Obviously it's not exactly 0.3, but it's certainly consistent. So here we have to show that it falls to 37% in a time that's consistent with the numbers. The time constant is RC, and we have a 3 kilo ohm resistor and a 100 microfarad capacitor. So if we do that calculation, we get an RC value of 0.3 seconds. And if we look at the graph and follow it through, we find that this value of 0.62 milliamps occurs at a time that's consistent with the other number, around about 0.24 or so of a second. So this value and this value are consistent. So what other graph would you use to confirm that this is an exponential curve? So if I is I0 e to the minus t over rc, then plotting the natural logs will give you the log of I0 minus t over rc. And you just rearrange that slightly to get it in the form of a straight line. So if you plot log of I up the side and t along the bottom, you should get a gradient of negative 1 over RC. Something like that. You don't really have to show the maths of this, you just have to demonstrate that you know that you're going to need to plot the log versus t, and that should give you a straight line. Pion radiotherapy is a new form of cancer treatment that has been extensively investigated for tumours of the brain. Pions are short-lived subatomic particles and belong to a group called mesons. The following table lists some quarks and their charge details. Okay, so we've got the up quark at plus 2/3, the down quark at minus 1/3, the strange quark at minus 1/3, and the charm quark at plus 2/3. So which quark combination could make a pi plus particle? We're looking for some combination that gives you charge of plus 1. So if we look at each particle, we've got up, up, down for this first one, which gives a charge of 1. We've got, oh crap, that's wrong, sorry, that's also plus 1 because those are antiparticles, those should all be pluses. Here we've got 3 anti-down quarks, which means that down is minus 1/3, so these are all plus 1/3, so they give a total charge of plus 1. Here we have an up and an anti-down, which gives you plus 2/3 plus another 1/3, which again is plus 1. Here we have a strange and anti-charm, which gives us minus 1/3 plus another negative 2/3, giving us a charge of minus 1. So it says on the list below, circle the combination which could correspond to a pion, a pi plus, and we're told the properties of the pi plus. We're told up here that the pi is a meson, and mesons are quark-antiquark pairs. So we come down to this table, we can immediately rule out these two. Okay, these are baryons because they're quark triplets. These two are quark-antiquark pairs, and only one of them has the correct charge. So this is our answer. So we're now asked to calculate the mass of the pion. If it's 0.14 GeV over c squared, what is that in kilograms? So we just need to do this calculation of 0.14 GeV over c squared, only do it in SI units, and that will give us an answer in kilograms. So that's going to be 0.14 giga 10 to the 9 times 1 electron volt. That's going to give us 0.14 giga electron volts, only now in SI. And we're dividing that by c squared. So don't forget to square it. Easy mistake to make. And that gives us 2.48 times 10 to the minus 28 kilograms. Okay, so here you're asked to explain the role of electric and magnetic fields in a cyclotron. And we remember that there's a reversing electric field that happens between the Ds, and that allows the particles to accelerate in the gap between the Ds as they cross the path. And that will be given by W equals QV each time they cross. Now obviously you're going to need to explain this in words. Then there's the magnetic force on the particles as they move through this zone, causing them to move in a circle, and the force of the magnetic force on them is going to be B times Q times V, and that's equal to the centripetal force required to make them move in a circle, mv squared over r. And again, you need to explain that in words. So when pions are used to treat brain tumours, they are slowed by the tissue in the brain and cause little damage, When a pion is moving very slowly, it may be absorbed by the nucleus of an atom. The atom nucleus becomes unstable and breaks up into several fragments. Explain why these fragments shoot out in all directions. Okay, so you're going to need to explain about conservation of momentum. We're told that the pions are moving very slowly by the time they're absorbed by the atom, so we can assume that we start with an object that has zero momentum with the pion absorbed, and then that the fragments of that thing shoot off in opposite directions, so that the vector sum of their momenta goes back to zero. That's really what you're trying to demonstrate, because momentum equals nothing at the beginning, so we would expect those fragments to equal nothing at the end when you add all their momenta values together. Total momentum before equals total momentum after, and before it was nothing, so after it's nothing. So you've got a little vector sum down here showing that the momentum of A plus momentum of B plus momentum of C should go back to zero. Obviously you can't, they're not told there are 3 items, so this is just a generalization. Photograph shows the track of a positively charged particle either side of a lead plate. The particle was deflected by a magnetic field of magnetic flux density 1.5 Tesla. The field is perpendicular to the plane of the photograph. Estimate the actual radius of the track above the lead plate. Okay, this looks like Anderson's photograph of the discovery of the positron, but we don't need to know that. We know it's a positively charged particle and it's either side of this lead plate. This is an estimation thing, so this will be why the front of the paper says you need a ruler, because you have to use the details they give us about the lead plate being 6 millimeters thick to make an estimate of other distances on this diagram. So what you're going to do is try and put in a couple of tangents to this diagram. It's almost purely vertical here, so that would be a good place to start, that way. And it's sort of going this way here. And that'll give you a rough estimate then of the radius if you measure that distance with your ruler. And that's based on the fact that this plate in the middle is 6 millimeters across, so whatever you get as a distance, you need to scale it up using the information of how far 6 millimeters is, or indeed measure out that distance in steps along this to see how many times 6 millimeters you've got. Okay, so the mark scheme says that this actual measurement should be somewhere between 4 and 5 millimeters, so that means you've got a little bit of conversion to do. They say you should be measuring this radius to be between 32 and 38 millimeters, which means that your conversion should be somewhere between a radius of about 38 and 57 millimeters. Okay, just do your best. So we're asked to calculate the momentum of the particle above the lead plate. Remember, we've got now a radius coming in from the previous answer of about 47 millimeters. So we've got R 47 millimeters, and BQV will equal mv squared over R. Consequently, BQ will equal mv over R. Remember, this is just magnetic force is the centripetal force being provided. So BQR equals mv, which is the momentum. So if we can find BQR, then we're finding the momentum. So we got 1.5 Tesla times 1.6 times 10 to the minus 19, the charge on the thing, times 47 millimeters. And that gives me 1.13 times 10 to the minus 20 kilogram meter per second. Don't forget your units. So we're asked to explain whether or not the particle is moving up or down through the lead plate. And so crucially, it's less curved before the plate, on the underside, and more curved on the top side. And if momentum is proportional to r, which it is, then the one with the bigger radius of curvature, the less curved, will be the one with the higher momentum. So if we've got higher momentum on the lower side, lower momentum on the top side, this had to be going up, because it can't gain energy and therefore momentum. Therefore the direction has to be upwards. And we're asked to indicate the direction of the magnetic field, so you need to do Fleming's left-hand rule here. So we've got a positive particle heading upwards, and it's experiencing a force that way. So positive particle going this way is the same as current going that way, because current flows from positive to negative. It's experiencing a force like this. So if we get our left hand, well, we can only get our fingers to line up correctly if the magnetic field is into the page. So we're asked to calculate the speed of the positron while it's moving above the lead plate. Now we already have its momentum from the previous part. So if we divide the momentum by the mass, we should get the velocity. You need to recognize obviously that the positron will have the same mass as the electron, because it's the electron's antiparticle. And you just get that value from your formula sheet and calculate. And we get this answer of 1.24 times 10 to the 10 meters per second. And that's mental, so not surprisingly we have a thing that says comment on your answer. And so what's going on here is that it's above the speed of light. That simply can't be possible. So the mass of the particle must be greater than its normal value due to its relativistic speed. And that's it. Woohoo!